I'm Nick.
I'm Caleb, and this is OPTI 380, Intermediate Optics Lab, lab number 7, Michelson Interferometer applications, and our TA is Susie. So we used a digital caliper to get an initial arbitrary position on the micrometer, and then we collapsed 125 fringes, and then took a final measurement to get the calibration factor.
To calculate the calibration factor, we multiplied the movement of the source, which should be the number of fringes collapsed times the provided source wavelength, and divided by the difference in the caliper readings of the micrometer position.
So this had a similar setup to the first part where we have a source and we're sending it through the interferometer and we want to calculate the wavelength. So we collapsed fringes and took the initial and final position of the micrometer. And then we can calculate wavelength from the distance moved and number of fringes collapsed. For measuring wavelength of the mercury and sodium sources, we found there to be around 10% error for the mercury source and around 7% error for the sodium source. So here Nick is trying to find the difference in wavelengths for the sodium doublet, and you do this by finding the difference in position of wavelength where there's a null and you can't really see the fringes anymore in the interferometer output. And finding delta lambda for the sodium doublet experiment, there was around a 66% error where we got a change in wavelength of 0.198.
For the fourth experiment, we have a similar setup to the calibration experiment, except now there's a vacuum chamber here between the moving mirror and the source. And the purpose of that is to have a variable pressure within there. So we use this device to alter the pressure and observe the collapsing and expanding of the interference pattern here. And from that we can derive a function for refractive index as it changes with pressure.
Through counting the number of fringes cycled through with a pressure change, it is possible to create a model to predict the refractive index at a specific pressure. And since we know the wavelength of the laser and it's possible to measure the distance of the vacuum, we can use this equation that has this relationship. And so that's the trend line of the expected pressure, or the expected refractive index per pressure.